Hi there. This supplementary video is to help you get ready to do assignment 4. And in assignment 4, you'll be learning how to use WECA's experimenter. And you'll also be doing some experiments and thinking about differences in performance and how confident you can be in your observation of them. So in class, we talked about confidence intervals a couple of times already. And in the assignment, you're going to compute a confidence interval by hand. And you're going to do this on your project data set. Now, in order to do this confidence interval, the way that it is described in the book, which is also what you see illustrated here on this slide, you really have to be computing this for a classification problem. What you should do then, to do this in the most simple way, if your project is about a numeric prediction problem where the class value is a number, what you should do for this assignment is transform it into a binary variable. So if you just pick a threshold, and probably the most convenient threshold would be the average value or the median value, which is the middle value, then everything above that threshold would be the positive class and everything else would be the negative class. Then when you do your cross-validation experiment, and in order to do that you will have had to have created trained test pairs for a cross-validation. There's a separate YouTube video about that, which Shri will have pointed you to in his guest lecture. So hopefully you've already seen that and you are already familiar with that, and you'll be starting the part of the assignment relevant for this video after you have already created those trained test pairs for your project. So, you'll have a performance value for each fold. You'll compute an average value across those. So that average value is the middle of your confidence interval. And now you're going to compute the upper end and the lower end. And you'll see that there's a plus or minus here in the equation. So the version of this equation where you use the plus is how you compute the confidence interval on the right-hand side of your average performance, and when you use the minus, you compute the lower end of that confidence interval. And you get to decide how confident do you want to be, and there in the book you'll find a table of separate z-scores that are related to different confidence levels. And the reason why we can compute these confidence levels is because within the normal distribution we know what percentage of data should fall within X number of standard deviations from the mean, and so then we can say, so one standard deviation from the mean, we should see 65% of our data. So if we just wanted to be 65% sure, then we would the distance from the mean would be one standard deviation. So what we're essentially trying to compute here is for different levels of confidence, and you're going to be working with a 90% confidence interval, z-score 1.65, and the z is to plug into this equation so that you use, so that what you compute in the end is equivalent to, I'm X confident that percentage of data is within, this distance from the mean value. And so in order to get that, the equation is also working in the other parts of the normal distribution, so that it's the normal distribution that you're using to refer to average and standard deviation and getting, within certain distance from that value. So it's all kind of folded into this equation. So you can see the derivation very carefully for this equation in the book. I'm not going to require you to understand step by step how it's derived. I just want you to kind of understand what it is that you're trying to do. So we're going to adapt the 90% confidence interval. That means there's a 5% chance that the actual value that you're estimating with the average actually falls lower than the lower end of the confidence interval, and another 5% chance that the actual value might fall outside of the upper end of this confidence interval. So F is a percentage of success. Where does that come from? Well, after you've done your cross-validation and you've got the performance value on each fold, then when you average across those, the average value you get is F. Now, N is the number of trials. And normally when we compute confidence intervals, N is the number of folds. But if you look at the derivation in the textbook, it's actually different. What it's doing is it's counting every one of your instances as an observation, and where it's either correct or incorrect, and so then the F is the percentage of correct classifications over your whole set. But you can tell that actually the percentage of correct classifications over your whole set is really the same as averaging the percentage from each of the 5 folds, since the same number of instances are in each fold. So you can compute F through your cross-validation by averaging across the performance from all your folds, but the N that you're going to use in the assignment is the number of instances. And the reason why I'm asking you to do the confidence interval that way is because if you get stuck, I want you to be able to use the book as a guide. And so I ask people on this assignment to do the confidence interval exactly as it's described in the book. So there's an example that you can see of what it would look like for a particular performance value where the observed average performance is 75% and the number of instances is 1,000 and the confidence interval is 90%, which corresponds to a z-value of 1.65. And now if you plug these into the equation, you should get the confidence interval that you see there, that the lower end is 0.727 and the upper end is 0.773, and you can see that those numbers are equidistant from 0.75, which is the observed average. So what does this mean? It means that if we have observed an average performance of 75% over 1,000 intervals, 1,000 observations, then we can be 90% sure that the real average that this is the real performance value that this is an estimate of is between 0.727 and 0.773. Okay, so now that you kind of understand how you compute confidence intervals around a performance average for one experiment, then you can think about what does it mean that, say, naive Bayes performed better than SMO or vice versa. Well, you can see the observed average of each of these, and you might just assume that the one that's higher is better than the one that's lower. But how confident are we that that's really true? We know that that we can only be 90% sure that a performance value is within a certain interval around the observed average. So if we compute a confidence interval around the average of the baseline, so the lower thing that we're comparing to, then if we want to be sure at the level of confidence that we have used to construct our confidence intervals that the higher value is actually higher than the observed lower value, it has to be outside of that confidence interval. So the only way that we can be 90% sure that the higher observed value is actually higher than the lower observed value is if its amount higher is higher than the distance between the observed average and the upper end of the confidence interval. Now, you can do a significance test by hand by computing confidence intervals and looking at whether the observed average of the higher value falls outside of the confidence interval or not, or you can do a significance test in the experimenter, or you can do it in Excel or some statistical package like Minitab, which CMU has a site license for, or any other statistical package that you might be familiar with. Now, for assignment 4, you are going to use the experimenter in the second half of the assignment. In the first half, you are going to compute a confidence interval by hand, and then you're going to do an error analysis on one fold of your data set. But right now I want to talk to you about the experimenter. So here's what the experimenter looks like. When you open it up, the first thing you should do is click the New button. Make sure that it's on the setting for simple. That's the only usage of the experimenter that we're going to actually learn in this course. Now, you can, if you want, save the results of the experiment, what's going on behind the scenes, in a file, and you can set that up the way that you see here. But what I've noticed over the semesters that I've taught this course is that some students' laptops are configured in such a way that for whatever reason they don't have permission to save this file. I don't know why that would be the case, but if that's true of your setup on your laptop, then don't worry about saving the file. Just don't save it. You don't have to. I'll show you that you actually don't have to have saved that in order to use the experimenter. So okay, so this just shows that you can save a file. Okay, so then there are two main things that you have to configure here on the front panel. One is that you have to give it the data sets that it's going to use. You should always load ARFF files, and the assumption is going to be that whatever is the last attribute in the attribute lists is the attribute that's the class value. So if that's not true, you're going to run into problems, and so then you're going to have to reconfigure your ARFF files so that that's true, because there's no place on the experimenter where it asks you what is the class value. It just assumes that that's where it is. So I'm just letting you know. Okay, so if you can load a file here. Now the file that I've just loaded is for a classification problem, and so I am going to set classification on the front panel. When you do the experiment in assignment 4, you're actually going to be doing a regression problem. So instead of classification as the radio button setting, you would set regression. Now, you should set the number of repetitions to 1. By default, it's 10. That means it's going to run the experiment 10 different times, each time with a different randomization for the cross-validation. And that's a very nice, careful way of validating that your experiment would come out the same way if you did it over and over again, that the result that you got is not random. But it takes a lot of time, and it's not really a good use of your time right now, so I suggest setting it to 1. So the final thing that you need to do on this panel is to tell the experimenter which algorithms it should use for its experiment. So it's going to give you this widget that you see with a choose button. Now this choose button is just exactly the same as the one that you have on the classify panel. So everything that you can do to set up for an experiment on the classify panel, you can do here through this choose button on the experimenter. So later, when we learn how to set up on the classify panel experiments that include lots of different kinds of pre and post processing, you could do all of those different specific configurations for each setup that you want to test here in the experimenter. So keep that in mind, because over time when you use the experimenter, you'll want to be able to configure it in various ways like this. Okay, so here I've set it up with 3 different learning approaches. And so I've got one data set, I've got 3 learning approaches. Now I'm going to click to go to the Run tab. I'm going to click Start to run the experiment. And when I run it, it should say there were 0 errors. If it stops before it gets to the place where it says finished, there were 0 errors, then there was a problem with how it was configured on the setup panel. So you should go back and see which part of the instructions you may not have followed. Hopefully you don't have that problem, so you click Analyze to go to the Analyze panel. Now if you saved the results as you went along, if you configured to save to a file on the front panel, then you can load that file by clicking this File button. But if you didn't do that, then you can still analyze the results of whatever was the last experiment you ran by clicking instead on the Experiment button. Okay, once you have told the Analyze panel which experiment you want to analyze, then there are lots of things you have to configure. You have to click Select for the row, for the column. You have to tell it what you're evaluating. Now here we did a classification problem, so we are going to pick the kappa statistic as what we're going to compare. But if you, for the assignment, for assignment 4, since you're going to be doing a regression problem in the second half of the assignment using the experimenter, instead you were going to compare the correlation coefficient. Now you can see here I have set the row to be the data set. There was one data set that I loaded, and the column I have set to be the algorithms, or it's going to be called scheme in that menu. So then you can see here I've got one row, and that's the data set, and I've got 3 columns because I had loaded 3 different algorithms. And you can see here on the key which algorithms each column corresponds to. And so in the row next to the data set, you can see the performance values. And since I have set kappa as my comparison field, these are going to be kappa values. Now you can see the arrow is pointing to select test base. And so that's telling me what's the leftmost column going to be. And I can pick from any of the columns. So here you can see it's not in the 1, 2, 3 order. I picked number 2 as what I'm comparing to. So then everything to the right is being compared to the thing on the left. And if I wanted to, let's say, compare 1 and 3, I can't do that with this test setup that you see here configured. I would have to change what the base was. I could change it to 1, and then I'll be able to see in the column corresponding to 3 the comparison of that. Now, when I perform the test, I didn't have a slide where I showed pointing to that, but you can see down there at the bottom on the right at the button that says perform test, and actually what you see, oh, that's left, sorry about that, bottom left is where the perform test button is. On the right, I've already been showing you this table where the analysis has already actually been run. So you wouldn't see the, what you see here on the right until after you've clicked on perform test. Now you can see here we've got these numbers. These correspond to the kappas for the algorithms that correspond to the columns applied to the data set that corresponds to the row. And you can already see that naive Bayes was worse than what's labeled here as function, which is SMO, and trees is better, and that's J48, or decision trees. And you see these little annotations that are to the right of the numbers. If there's an annotation there, it means that the difference that you observe is statistically significant. In other words, 0.16 and 0.53 both fall outside of the confidence interval around 0.37. So star means significantly less, V means significantly more, but you don't have to remember that, because if 0.16 is less than 0.37, and if it's significantly different, it can only be significantly less since it's less and not more. Similarly, 0.53 is greater than 0.37, so if it's significantly different, it has to be significantly higher. So that's how we use this interface. Now, if we wanted to do some additional analyses on our data, we can use that file that we saved. You can open it up and take a look at it as a CSV file, and it will give you lots of information like what data set, which run of that data set, which fold of which run. So, you know, if we're running a cross-validation, and if we had several different data sets, and you can see here key scheme, that's the settings on the algorithm, and then we've got what time was it run, we've, you know, lots of things to the right. Now, if we wanted to be able to, you can even see percent correct there in column M, and then over to the right of that, you'll have kappa. So even things that you didn't pick to display when you did the analysis, they will have been recorded in this file, and you can get to them. So you could load this file into any statistical analysis package and do more statistical analyses. If you've taken applied statistics, then there are things that you might be interested in checking. And if you wanted to learn more about that, these packages also have documentation that you can find on the web. So for example, let's say I want to know if, you can see overall whether there was a difference in how the data sets performed, or which algorithm was used, or if the difference in performance varied by a data set. But in this particular analysis, you can see, if you know how to read these things, and you would know if you had taken applied statistics, otherwise it probably doesn't make a lot of sense to you. Actually, none of the differences were significant. But you can see here on the p-value, p-value is the probability of difference. So if the p-value is less than 0.05, that means that the average of what you're comparing is outside of a 90% confidence interval around the baseline that it's being compared to. So if this had been significant, if we had seen less than 0.05 there on the first row, that would mean that the performance value of the different data sets on average was different. But if it was only different for one algorithm, then you would see that the interaction term down 2 from that, key data set times key scheme, would have been significant, but it's not. So that means whatever result I have for data set and for scheme, which is the algorithm, holds across all of the conditions that it's being crossed by. But this is not a class on applied statistics, so if that's new to you, that's probably not enough information to really understand it. But if you want to learn more about it, you can always come and talk to us during office hours. So for the last part of assignment 4, you will be doing a regression problem. So you will use the experimenter, and you can use all of what I just led you through, but you're going to do the version of it for regression instead of for classification. So you'll set regression on the front panel and correlation coefficient as the comparison field. Okay, so hopefully you will be able to get started on assignment 4, and again, come to office hours if you have problems.